You can start.
Okay. Okay, so the topic of my presentation is word vector representations and applications. So this topic was already partly covered by our colleague Sergei Shelpuk this morning, but I will try to bring some complements. So it's like, if you want, the second part of his talk. So at the beginning, I will just recall some things that Sergei already said. Then I will focus more on applications of word representations. So the two big applications are machine translation and sentiment analysis. Machine translation is like Google Translate, and sentiment analysis, I will say you later what it is. And then in the third part, I will explain a little about the algorithm GLOVE. I will say more details about this algorithm. And the fourth part will be like a promotional part about my activity in Kyiv of deep learning meetup. So let's start. So what is word vector representations? You have a set of words, a vocabulary of, for example, the English language, or Ukrainian, why not? And you want to have all these words into a vector space, such that if two words have similar meanings or near meanings, you want that their vector representations are near each other. So if the words are near each other, their vectors are near each other too. So this is a property that you want to have. So why we want to have this kind of properties is to make a connection between humans and computers. So humans, they think in terms of words and meaning, and computers, they think in terms of vectors. So when we make these connections, we get better like artificial intelligence. And also we get better prediction algorithm, like in machine learning, linear regression. And you hope that this algorithm will work better because these vectors will be more faithful to the meaning of words. And in practice, it really works better. So for example yes, I will go quickly. For example, if you have cat, dog, mouse, house, you think that the vector, yes. You think that the vector that will be the more far is house, because cat, mouse, and dog are animals, and house is not an animal. So how you get this can maybe say a word, so this is what Sergei explained this morning, maybe say a word about how you get this picture. It's you have that word vectors, they are usually vectors in 300-dimensional space, and this picture is in 2 dimensions, and so how you get a 2-dimension picture from 300 dimension? In this visualization, we use a technical TSNE, where this method preserves the cluster of points. It preserves the relative distance between points. So if you are interested, you can explore this method further. Another good thing about word vector representation is that you have parallelism. For example, if you have king plus woman minus man, you expect to get a queen. I don't know if the picture is clear for everyone. Maybe it's too small. So you have here king, man, woman, and here you have queen. And you have that king plus woman minus man is near queen. And so it means that your vector representation respects analogies and parallelism between concepts. And when you want to visualize this kind of parallelism, you need to use another visualization technique called PCA, which is a kind of eigenvalues decomposition, if you know a little about mathematics. And why you should use this visualization and not TSNE, the other visualization, is because here you want to preserve, you want a linear projection, so you want to preserve parallelism. While in the other picture, you wanted to preserve, you wanted to preserve clusters of points. So it's 2 different things. So when you want to visualize data, you need sometimes to use different techniques depending on what you want to do. So what is the idea behind all these algorithms? It's just so you have this proverb by John Firth that you know a word by the company it keeps. It is what Sergei explained this morning. And so the idea is that when 2 words are near each other very often in your data, in your text data, you hope that their meaning will be next to each other. So the idea is that you get meaning from statistics. This is the idea of these methods. On how you get this miracle of getting meaning from statistics, you need to use very big data sets. For example, Google News, people, they use Google News, it's 100 billion words. Or Wikipedia, it's 100 million words. And you have other data sets that I will use later. Oh, here we don't see at all. So so now I go to applications. How we get to zoom? So for example, yes, here we see better. For example, once you have your map of your two different languages, you can make translations, like Google Translate, a kind of a homemade Google Translate with this method. So for example, you have here your map of your French language with maybe 4 words, cyclone, Ukraine, any word you like. And then you want to construct a function to your English vocabulary. So you have you construct another map, another word representation for the English language. And what will be your Google Translate? It will be your function from your French space to your English space, for example. And this is what we have here. How we get full screen again? Okay, thank you. So this method is very standard. It exists since at least 2008. But one guy refined this method very well. It's Mikolov. At that time, he was in Google. And he made so he wrote a paper with his colleagues to make an English to Spanish translator. So this is what he made. And me, what I made at home. I tried to make a French to English translator and a French to Spanish translator. And he had better conditions because he had Google News. On me, I didn't have access to Google News. I just had access to Wikipedia. But we still had similar data sets called MT11. So it's MT11 is for Machine Translation 2011. So every year you have competitions, and this paper used the 2011 set. So how do you make this map? We just, for the training sets, we use the 5,000 most common words in the English language, and we look at their Google Translates in Spanish. So we use some existing translator, and yes, Google, yes, it's misleading. So we take a dictionary, which tells you the translation, like a handmade, a normal dictionary, which gives you the translation between English to Spanish. And you use it as your training sets. And then you train linear transformation to generalize to all your vocabulary. So yes, so there are some notations, but basically we just do a linear kind of linear regression with this from between these two vector space. And this is what we do. So I will not explain these notations. Maybe it's not necessary. And then how we make the test, how we test the accuracy of the dictionary. We look at the next 1,000 most common words. And if we, like the first accuracy is if we get the good translation at the first attempt. And the 5 accuracy is when we get the good translation after 5 attempts. So we have 2 ways to do it. And me, I did from French to English and French to Spanish. So what are the results? So Mikolov, he gets with Google News very good accuracy, and with MT11 slightly less. And me, I get even worse. I get no result with Wikipedia, and not so bad result with MT11. So why I show you these things is because Wikipedia in general, if you look at the literature on language processing, they will in general use Wikipedia to do this. But me, I didn't have good experience with Wikipedia, and other people too. So I looked in forums and everything, and many people didn't have good experience with Wikipedia. So what I want to tell you is that Wikipedia sometimes is not the best option. And so yeah, so I had a very emotional reaction, and so it allows me to make transition to sentiment analysis. Because what is sentiment analysis is when you want the computer to understand emotions. So this is mainly like the main difference between the computer and the human is that the computer now, he doesn't understand the emotions, but we are working on it. And how we study this problem, we use a toy problem, which is called sentiment analysis of movie reviews. Because, for example, how it works, it's like people, they go to a movie, and then they go home, and they write their opinion about the movie. So they're not very emotional because they feel like they wasted their evening if it's negative, or they feel like they had an awesome night. And so it's very emotional problem. And so, but it also has a lot of business applications, commercial applications. And you have a lot of companies which make money just with this sentiment analysis. For example, in marketing, or in if you want to analyze the reputation of your brand, or in finance. Even in finance, if you can look on Twitter and see if the mood of traders and things like this. So it's a very effective method. So just to give you an example of a review, why it's a difficult problem. For example, if you look at this review, this movie contains everything you'd expect, but nothing more. It is very hard to determine if this review is positive or negative. And especially if you look word by word, it's like almost impossible to guess if it's positive or negative. So it's a very difficult problem. But if you have vector representation, it becomes a very easy problem. Enfin, not so easy, but still quite good problem. Because with this movie data set, once you already have vectors, a very naive method to get to make sentiment analysis, you take a review or word by word, and then you make the average of all the vectors of your review, and it gives you a vector for all your review. Each review has one vector, which is the average of all the words of the reviews. And if you give this to the standard classifier, like random forest or support vector machine, your favorite classifier, you get a very good accuracy, for example, 83%. So it's like very honest results for a very simple method. But of course, if you want to get more than 83%, it becomes much more difficult, because when you do this kind of averaging, you lose the order of your words, because when you do A plus B, the same as B plus A. So you lose a lot of information by doing this naive method, but it's still, I think, a very honest method. Then we can use more sophisticated methods for this problem. So you see that this problem really stimulates a lot of research. For example, maybe you heard about convolutional neural networks. It's a prediction algorithm that is mostly used in image classification. So, for example, if you want to detect cats or dogs on your pictures. And you can also use this. So why images are interesting? In images, it's for a computer, an image is just a matrix of numbers. So it's a two-dimensional matrix. And how you can get a two-dimensional matrix from a text? For example, you have this review, the cat sat on the mat. Well, it doesn't look like a review, but why not? And you put here, I have this. You put here your vectors in columns. Each column you put your vector. And then it gives you a kind of table, a 2x2 matrix, a two-dimensional matrix. And so it looks like a kind of picture. And then you can give it to the algorithm, and you hope that it works. But unfortunately, it's not so easy with this data set, that's the IMDb. So if maybe you know it, it's the Internet Movie Database Review. So it is a classical data set. But this data set is very vicious, because the difference between reviews and images is that in images, your resolution is kind of fixed, so your matrix is already known. But if you look at text, the length of the text is very variable. Some people, they can just write a very short review. Other people, they can write a very long review. And it really affects, it's a very important variable. So it's more difficult to play with this, with text than with images. And so for example, in this dataset, you have like 2,000 words per review. So it's like you have a picture with 2,000 pixels on one, no, 2,000 times 300 pixels. So it's really a big table. So it gets too slow for normal computers. And so I just wanted to show this method because to give you maybe some inspiration. But for me, I was not very successful with it. So, so if you want to play, you can try. But it's really time-consuming because your training is very slow. So what other, maybe just to mention, there are a lot of applications for word embedding. So if you want maybe to start a business from this, it's very easy. Other people already did it. Yes, it was shown by this image, was shown by Sergey this morning, but it was not Italy, it was Germany. So here, if you do pizza plus Japan minus Italy, you get sushi, which is something more maybe familiar to everyone. And I think it's a very good idea, because if you think on Google, you can add words when you write your query on Google. But to subtract words, this functionality is still not available, but I think it will happen. And so another application is for recommendation systems for online shops, because once you know the similarity between your words, for example, if you like I don't know jeans, maybe you will like I don't know shirt, like something that is similar to your previous purchase. So this word embeddings also have applications in marketing. Now, in the time that I have, yes, I have some time, I will give you more details about this algorithm. So Sergey this morning, he explained how to build a co-occurrence matrix. So what is a co-occurrence matrix? So this is what he explained this morning, is you take a word that you like, and you look at the context window around your words. For example, the word Ukraine, and the context window of size 2 will take the 2 nearest neighbors of your like your favorite word. And from this, it gives you a number, xig, which is the number of times the word I and G co-occur in the same window. And once you have this number, you put this number in a matrix, X, yes, and which is symmetric, because this property is symmetric. And then you get what is called a co-occurrence matrix. So this is what, I don't know, maybe I make who didn't come to the talk of Sergey this morning? Maybe I will know. Who didn't come? 1, 2, 3. So all the rest were, okay. So maybe I can go faster. So the first time is to construct this matrix. Second time is to factorize this matrix. And to factorize this matrix, we use a method called gram factorization, maybe, or something. I don't know how it's called in the literature, but it is not SVD. It is wrong. You said it's SVD. It was a mistake. It is another kind of factorization. The factorization. So this is why maybe, Sergey, you need to be concentrated, because I will explain what factorization is. So this factorization, you have your symmetric matrix. So once you have a symmetric matrix, maybe if you did some mathematics in your childhood, you know that a symmetric matrix is sometimes a gram matrix. It represents the scalar products of a family of vectors. And you know that the scalar product is a symmetric operation. So this is why your matrix is symmetric. So this is why we can think, I think it's a legitimate opinion, to have this scalar product. And so we think we try this very naive factorization to just extract from a scalar vectors from your matrix with scalar product. But this idea doesn't work in practice. So we try some cooking, and we think that we note that if we have f, a function f that is scalar, which means that it only manipulates numbers. So a scalar function applied to a matrix is just f to each of your items of your matrix. So you notice that if you apply any function, your matrix is still symmetric. So you can try again with another function. So here you will put f of xig, and you will try a f that gives you your good factorization. Or what happens to the... I don't know, it's good. So how we do it? It's maybe probably the hardest part of the talk, so I will try to be slow. So we look at 3 words. So first we take 2 words, I and G, for example, fruit and house, 2 words. And you consider then a third word like apple. And you notice, if you look at your matrix, you see that xik over xjk is large if you take fruit, house, and apple, because an apple is a fruit, so apple is nearer to fruit than it is to house. So your ratio will be large, because xik will be a very large number, and xjk will be a smaller number relatively to xik. So you notice you make this first observation. Second observation, if you take a word like room, which is room is near house and it's far from apple, so you notice that you have the opposite phenomenon. If you look at your tables, you see that your ratio xik over xjk is small because room, xjk will be very large and xik will be small. And on the other hand, if you take three completely unrelated words, like fruit, house, and sky, you will see that this ratio is around 1. So why this this observation is good? Because it gives you the intuition that this ratio is important. So you think, instead of just looking at if xik, like here, if xij, you look also at f of xik over xjk, because you hope that it will be something magical. And if you try to seek how to combine scalar product with 3 vectors, with something that looks like a ratio, you get something, you feel that you should do vi minus vj scalar vk. Because the minus is like a ratio, and and the k is like in the 2 parts. So you feel you don't have so much option to try a formula. And so it gives you a second constraint, a second formula. And if you also use the first formula is this one, vik equals if xik. If you write this formula twice and you make the subtraction, then you realize that your function is just a logarithm, because it gives you a map between, it transforms the multiplication, like here the division, into a subtraction. So the only, more or less, the only map that can do this is the logarithm. So it gives you the idea to try the logarithm and see if it works. And so you think of f equals logarithm. So you try to factorize the logarithm of your matrix. And if you do it, of course, you cannot do it, you cannot make an exact computation because its numbers are maybe. You mean the? The dimension of the vectors, yes. Yes, it's very small, like D is 300. Yes. So, because you have a lot, it's gram matrix. Because you see that your number, this is a scalar. This is a scalar product of 2 different vectors. So it's a number. So it doesn't matter the dimension. What determines the dimension of your matrix, your dimension of the matrix is not connected to the dimension of your vectors. You reduce, yes, yes, because actually the dimension of your vectors is what is called a hyperparameter. So it is a parameter that you choose by yourself for as you like. You can do this with 2-dimensional word vectors. But the thing is that you take a big space because you want to have a lot of degrees of freedoms. But you don't want a too big space because then it makes your computation too complicated. So, so yes, it's a very good question. The dimension of the vectors is completely disconnected to the dimension of your matrix. Because what determines the dimension of your matrix is the number of vectors you consider. So you can have a very, very big gram matrix with just 2 dimensions, or even 1 dimension, even 1-dimensional vectors. Yeah, but it will be not, but 2, I think 2, you see that with 2, you just take vectors in the plan, many vectors in the plan, and it will give you a very big gram matrix, because it will compute all the correlation between your vectors. So is it clear? Okay, thank you. Maybe another. Yes. Apple and? Yes, but the thing is because you take a very large data set. So you hope that in your data set, the Apple company, it depends what is your data set. Your Apple company will, if you take a general text, will happen much less often than the apple that you eat. But it depends. This is why if you want to play with it, in general, it is recommended, well, it depends. But sometimes it is better to take your data sets to train your vectors on your data set. For example, if you want to study Apple company, like IT companies, or do something about IT, it's better if you take your training set, text about IT, like some blogs and something. So yes, another question?
If you don't mind, let's talk about ambiguous words.
My?
Ambiguous words, the words that have more than one meaning in English. English is rich with
Yes, yes.
Take the word suit, which in one connotation is closer to the word lawsuit. So
Mm-hmm.
they will have the same context.
Mm-hmm.
But then you can take the same word suit in another context, like costume. So
Mm-hmm.
it will be closer in the context to costume.
Mm-hmm.
So the vectors of all three words will be completely different. Will you ever be able to tell that in this so the word that you take isolated suit is closer to some other word?
When you mean when you have homonyms, like it's like apple, you mean that the same words can have completely different meanings.
So what do you do then?
I don't know. I will think about it.
Another question
Yes,
is
continue.
about
Yes.
morphology, because so the word house can also be a verb, right?
Yes, it's like connected to your first question. Once, one, you, once, one.
This is not about semantics now. This is about grammar now.
Ah, okay.
This is
Mm-hmm.
a different issue. It should be solved in a different way. So the question is, how do you solve this morphological issue?
No, but it's a good idea.
That would be one thing if you
I will
take
think
only
about.
nouns, for example, and you compare the context of nouns with context of other nouns. Then you can say that these two words are close to each other.
Uh-huh.
But when you're taking the word that and you don't know which part of speech in this context it is in this context, okay, you can't say that they are close.
But it depends. I mean, again, this is why I talk about applications, because it depends what you want to do. So you should tell me what do you want to do with this ambiguous
Translation or for classification or for
for
anything.
for
So actually the part of speech. Okay, but it will
but the thing is that this ambiguity should be plugged in your training set. For example, if you want to do classification like of sentiment of movie reviews, you hope that these problems will be inside your training set. So the computer, he will know because he will have experience. The thing is that you give experience to the computer.
if you don't take into account the part of speech, then you can actually be comparing nouns to verbs which cannot be compared.
Maybe I can ask some other questions.
Oh, yes.
Include
Yes.
speech tagging and some other linguistic mathematics in this method.
You mean to combine this? But I think that part of speech padding can be done with it. Yes, I guess that people did part of speech tagging with this. Yes, with this method. Yes, they use word vectors then to do part of speech tagging. I think yes. I think yes. I think yes. I will check. But it's a good question. I don't want to tell you something wrong, but I will find the paper and I will send it to you. Yes, the computer cannot detect these problems. No, but the thing is that you combine these word vectors with something else. I think that this is the answer. That you don't just do word vector and then you say, oh, the computer is stupid. No, you don't do this. You do your training. You have your training data. For example, for sentiment analysis or part of speech tagging, for whatever is your task, you teach the computer. It's not everything is in the word vectors. So you have ambiguity, but then you hope that this ambiguity will, because you see you have very different, well, I don't want to say something wrong, but I feel that, you have a lot of dimensions, like 300 dimensions. So maybe maybe this ambiguity is captured by the fact that your words, when people think about meaning or proximity, they think in one dimension. Well, you should think in 300 dimensions. So maybe from one aspect, the words are near, but from another, they are far. So you see that maybe this, I don't want to say something wrong, but I think it makes sense. And if you combine this with your training set, that your training set already has all these properties inside, then you hope that this will be reflected in your test sets. And I don't think that it's, why not, I mean. Okay, so we can continue. Any other question? We have time, huh? So yes. Any other question? No? So yes, so did you understand the factorization?
Yeah, well, the fact that I mentioned was that SVD doesn't work here, so that's fine.
Yes. Here it's not SVD. No, but you were right.
That's exactly what I told the one in
Yes. Sorry, I didn't understand the Russian. I just saw SVD on the. I was like, oh, but okay, sorry. Let's continue. So, but you were not right because there is SVD somewhere. So you see that this method is nice, is very nice. So for different reasons, good empirical performance. The cost function is similar to word2vec. So yes, what is word2vec? We said in the morning. It's another algorithm. It is made by Google. And so it is like the incumbent, how to say, the state of the art. This is the state of the art in the topic. And Glove came later, and it is like the two algorithms have similar performance. So another thing, what is nice, so yes, maybe you know latent semantic analysis, probably. So be careful that this is probably better than latent semantic. It inherits a lot of properties of latent semantic analysis. You still have co-occurrence matrix, like in some NLSA. And you also have this factorization with the logarithm. So it's really similar. So there are a lot of connections between the two, except that this factorization is SVD, so singular value decomposition. So it's like eigenvalues. Well, here it's another factorization. So yes, so I think now I finished. So maybe now for the 5 minutes that I have, maybe some 15 minutes. Oh, I have a lot of, maybe it's a little of advertising to finish, but very short. So yes, so now I'm involved in Kyiv about a meetup, so like a meeting, about a specialty called deep learning. So it's like convolutional neural networks or other stuff like that, things that Sergey talked a lot in this morning. So the frequency is every 2 weeks in Kyiv. I don't know if people here go to Kyiv, but if they want to come, maybe they can come for this meeting. So we have a lot of people around, so yes, a lot, more like 30 people, so it's decent attendance. And we have different people, we have experts, we have like tourists, and a lot of people in the middle. So we have regular talks, but we also now we develop two things. We have we try to make like some international collaboration with different meetups. So there are other meetups in Paris, in London, and we, for example, we recently had Mostapha Benhenda. Maybe you know him. So he's like a famous guy, and he was remotely with us from London. So it was a really nice thing. But we also have I think it's very good for education because we have a lot of tutorials. So we have tutorials about Theano and so on. Yes, if you don't know Theano, it's like a popular library of deep learning. So if you want to come, you just register to this website, and it's free and it's open. Okay, thank you for your question.
Okay, thank you for your presentation. Maybe no one have questions?
I would like to ask 2 questions. The first one concerns how do you choose a dimension of 300?
Yes, I did.
Do you know good heuristics or methods?
Why it's 300?
Yeah.
I don't know why, and I don't know if anyone knows.
Yeah.
But it is empirical. Basically, it's empirical because you have this kind of curve that the performance of your algorithm increase when you increase the dimension. But this function is concave. I don't know how to say it in English. Concave.
Yes.
So at some point, it has it's kind of plateau. It has like a plateau. And so you just take when it starts to plateau, and it's around 300.
Yes,
if you go more, then your performance is not good.
I understand. Just there are some situations where, depending on the subsets of words we are analyzing, different numbers of reduction performs better.
No, but it's a very good question because actually 300 is like the average number. But then it depends on your task. You are absolutely right. For example, when you do the machine translation, like Google, you need to use a larger dimension, like 1,000 or 800 dimensions
Sometimes
in one direction. I don't remember which one. And in the other, you can just stay with even less than maybe 200.
Yeah.
So it really depends on your task, and people, they do it by trial and error. So they try different things, and they find.
Yeah.
So it's a good question, of course, to try to understand this mysterious number.
I also saw some papers written about the dynamics of correlation between 2 words when we shift our dimension from 100 to 1,000 and so on.
Okay.
And the second one, in fact, the first step of your algorithm is maybe SVD, for example, to find these 300 dimensions. Or do you use another method, and which method could you recommend?
To find to find
This is a passive
300.
representation, yes.
So you don't
W.
know. You want to do a word vector. I understand your question. You want to construct these word vectors.
Yeah.
And you don't know that the good number is 300. How do you find it?
It doesn't matter for now. Just a message.
Yeah, you just want to do something, and you want to think what is the best dimension.
I do not care about the dimension for
What is your
now.
question?
I am asking because suppose that you want to find an embedding of a word to a vector, and then you using this very similar method for a second step. When you are getting this factorization of logarithms 1 plus x.
What do you mean that you reduce the dimension of your...
Twice. In fact, twice.
You mean that you start to construct vectors with a large dimension?
So we are using approximate methods for 2 times.
I understand what you mean. So you mean that we start with a very large dimension and we construct word vectors,
Yes.
and then we apply SVD or PCA, something like this.
Yes, or maybe neural networks and...
yes, to reduce the dimension. And then you find 300. Let me think. Yes, I will think.
Let it be, but then you are using again PCA. Does it really help to use the same method twice?
No, in general, if you apply PCA twice, so you apply PCA, and then but if you reapply it, you don't get better. I mean, what do you mean? You apply PCA once, and then just for fun, you apply it twice.
Yes.
I mean, do people do this in general? I mean, in general, do you do it in other situations?
And so also...
I don't think it works.
In fact, the second step is not a finding in your representation. We just want to proceed from the co-occurrence matrix to the matrix logarithms 1 plus x. And in fact, do we really need to find that vectors? Because we may calculate all we need in terms of our initial vectors.
So you mean once we have the co-occurrence matrix?
Once we know that this is logarithm, does we need to proceed further?
When you mean that we know that the good matrix is the logarithm of the co-occurrence,
yes.
Why do we care about the vectors?
Yes.
And then, let me think. Because the vectors have a smaller dimension, because your matrix is very big. As he said, the matrix is like millions millions of coordinates in your matrix, while your vector only has 300 dimensions.
And so computational.
This is why vectors are better, because it's a kind.
Computational.
It's a kind of yes, you are right. It's a good remark. It's a kind of dimensional reduction, dimensionality reduction. This kind
yes.
So this is why it's good, because you get smaller. And this is the whole point of this theory, because you know that, for example, you can represent word vectors. The very naive is like the one hot with 0001.
Yeah, I understand. So
when your matrix is a kind of the same, it has the same dimension. It's like millions, and so this is why we care about, because we want a more compact with smaller dimension, because then we apply machine learning algorithm, and in machine learning algorithm we like to have small dimension, because you know the curse of dimensionality.
Yeah, I understand.
So this is the point. But thank you for your question, because it really clarifies everything.
Thanks.
Okay, thank you for your report, and I have a question. Can you run this word-to-vec or GLOW algorithm in batches or online? Because when you are working with hundreds of millions of text and you have a vocabulary of millions of words because of errors, spelling errors or something else, you can't just load all of this into memory.
It's a good remark. It's with word2vec you can do it, but not with GLOW. So this is a weakness of GLOW, that with GLOW you need, you construct a matrix. But with word2vec, yes, because it's another algorithm. It's just by batches. Every time, so you can feed more text and get better vectors.
Okay, thank you.
Yes.
Okay, next question.
Can this algorithm to be applied to measure the sense of the sentence? For example, when we have the tail generation algorithms, can these word vectors used to be measured how much sense does this tail in general mean?
What do you want, excuse me?
To measure the, for example, when you have a system that generates tails,
Generates?
tails,
Tales.
fairy tales.
A fairy tale.
Yes, and to measure the
Like
sense.
poetry generation.
Yes, and to measure whether this whole tale makes any sense at all. For example,
So you want to generate your poetry with your favorite poetry algorithm, and then you want to evaluate your poetry.
Yes. How much does?
How can I? But how do you? What do you mean? It's a very hard topic. How do you measure the quality of a poem? It's a very difficult question. So if you have this indicator, then we can do something.
Questions?
So you said when you did the classification of the movie reviews, you did the averaging of the vectors in the paragraph.
Yes, yes.
Could you just, what happens if you just stack those vectors in a single large vector and do the SVM on that stuff without averaging?
What happens?
Have you tried that?
I didn't try it. I didn't dare to try it, but I should have tried it.
Yeah, but you still have that problem with different dimension, though,
It's
probably because
bigger, but I should have tried it. Yes.
Okay, that would be interesting, I guess.
Yes, yes. It's good remark.
Okay, one more questions. Okay, thank you, Mostapha. Okay. Now we will have a coffee break up to 25 minutes. Перерыв 25 минут.